everyone! Today I want to introduce you to some of the absolute coolest organisms on Earth, psychrophiles. The name literally means cold-loving. While normal cells freeze and die in extreme temperatures, these bacteria, fungi, and algae thrive in environments below 15 degrees Celsius, and some can even survive well below freezing. Now, they don't just tolerate the freeze, they actively require it. A psychrophile's ideal temperature for growth and reproduction is usually 15 degrees Celsius or lower, and they generally cannot survive if it climbs past 20 degrees Celsius. To them, normal room temperature is literally a deadly heat wave. So, where do you find these cold-loving creatures? They are thriving in places like deep ocean waters, glaciers, and polar regions like Antarctica. To maintain metabolic function at sub-zero temperatures, psychrophiles rely on a process called homeoviscous adaptation. In standard organisms, extreme cold causes the cellular membrane to undergo a phase transition from a fluid state to a rigid, non-functional crystalline gel. To counteract this, psychrophiles structurally modify their lipid bilayer. Let's look at the biochemistry. Saturated fatty acids have straight hydrocarbon chains that pack tightly together via van der Waals forces, rendering them rigid at low temperatures. Psychrophiles, however, synthesize a high ratio of unsaturated fatty acids. The introduction of cis double bonds creates distinct kinks or bends in these hydrocarbon chains. This steric hindrance prevents tight molecular packing, significantly lowering the membrane's transition temperature. By maintaining this high concentration of unsaturated lipids, psychrophiles ensure their membranes remain fluid, semi-permeable, and fully functional, even in freezing environments. Meet Psychromonas ingrahami, a remarkable bacterium isolated from Arctic deep-sea ice that pushes the absolute limits of biology. It holds a record for growing and reproducing at a staggering minus 12 degrees Celsius, well below the freezing point of water. At these sub-zero temperatures, molecular movement slows to a crawl, threatening to shut down cellular life. To fight this, P. ingrahami's metabolism relies on a masterpiece of cellular engineering, cold-adapted enzymes. While normal enzymes freeze and become rigid, the proteins inside this bacterium are highly flexible, acting like loose springs. This structural mobility allows them to bind to nutrients and catalyze chemical reactions with minimal activation energy. But this survival mechanism comes with a fatal trade-off. Because these proteins are so loose and fragile, they completely lose their shape and denature if temperatures rise even slightly above room temperature. So, how do psychrophiles actually make food or get energy when they are frozen solid inside ice or trapped in the pitch-black deep ocean? First, the phototrophs, the solar-powered producers. Microscopic psychrophilic algae living in polar seas can perform photosynthesis directly under or even inside the ice. They trap whatever tiny amounts of sunlight pierce through the frozen sheets, converting carbon dioxide into sugars, just like regular plants, acting as the foundation of the freezing polar food web. Second, the chemotrophs, the chemical eaters. Deep in the ocean or buried inside glaciers where sunlight can never reach, psychrophiles can't use photosynthesis. Instead, they rely on chemosynthesis. They extract energy by breaking down inorganic matter around them, like sulfur, iron, or methane, turning harsh minerals into usable cellular energy. And finally, the heterotrophs, the scavengers. There are also predatory or scavenging psychrophiles. They don't make food at all. Instead, they produce specialized cold-active enzymes that break down dissolved organic matter or dead organisms floating in the freezing water. All right, let's see how well you were paying attention. Here is your sub-zero pop quiz. Question 1. What does the word psychrophile literally translate to? Is it A, ice hater, B, cold-loving, or C, deep ocean? The correct answer is B, cold-loving. The name comes from the Greek words psychros, meaning cold, and philos, meaning loving. It perfectly describes organisms that are biologically hardwired to thrive in extreme sub-zero conditions. Question 2. To keep their cell membranes flexible in the freezing cold, psychrophiles pack them with what? A. Saturated fats like butter. B. Unsaturated fatty acids like olive oil. Or C. Sugars. The answer is B. Unsaturated fatty acids. Cold temperatures naturally make cell membranes freeze and turn rigid. Unsaturated fatty acids have structural kinks or bends in their chemical chains that prevent them from packing tightly together, keeping the membrane fluid and functioning, just like liquid olive oil in a refrigerator. Final question. What happens to a record-holding bacterium like Psychromonas ingrahami if you leave it out at normal room temperature? A. It reproduces faster. B. It goes to sleep. Or C. Its proteins unravel and it dies. The answer is C. Because psychrophiles evolved to stay highly flexible in freezing zones, their molecular bonds are incredibly fragile. When exposed to heat, even just room temperature, their weak structural bonds break, causing their vital enzymes to completely unravel, denature, and fail. How did you score? Whether you got 3 out of 3 or just learned something new today, you now know the secrets of the psychrophile. Thanks for watching, and we'll see you in the next deep dive into the wonders of our world.